Hey everybody, just a couple things to cover today. We're going to try to interpret this thing called s and another variable called r squared. So I guess I'll start off by just saying what those two things mean. So s is referring to the standard deviation, standard deviation of the residuals. So we're still looking at bivariate data, two variables plotted on like a scatter plot, or whenever you do statistics on two variables, you'll come up with this value called S. And again, that is the standard deviation of the residuals. R squared, the name for it is the coefficient. R squared is the coefficient of determination. So we should have a pretty good handle on what the standard deviation means. It's like, just the typical distance to a data set's mean. But in this case, we don't really have like a data set. We're looking at residuals instead of just one variable. And then the coefficient of determination, again, that is the r squared value. And we're going to go through a little example so that way we can explain where this value comes from and then interpret it. Without seeing it with any examples, it's kind of confusing, I think. So anyways, it's kind of how much error have we gotten rid of by creating a regression line. And so I've got this data right here for you. We got some y values. The y values are 2, 3, 5, 4, and 4. So the idea is if I was only given the y values and I didn't know their associated x values, what would be the best guess for another y value? Like if I was to add another value here, what would be my guess? Like where would it fall? And so the answer to that would be the average. The best guess without any other information would be the average. The best guess for these y values would be, again, the average. So the mean of this data set, is 3.6. Now, let me put it on a scatter plot and then draw that line. I think it'll make probably a little bit more sense. So I've got the scatter plot made, I think, on a calculator. Maybe let's go like this. So I got a y value of 2, and it's going to go add some labels here, 1, 2, 3, 4, and 5. So I got a y value of 2, and we're going to put that right here. My y value of 3 is going to go right here. My y value of 5 is going to go way up here. Then I've got a y value of 4 right here, and another y value of 4, and it's actually going to go right here. Fantastic. All right, so again, we're going to look at this two different ways, essentially. First way will be using no x values. So, gosh, I'm trying to think of the best way to kind of write this down for you. All right, so the coefficient of determination, it deals with residuals. So we'll do one column over here, residuals using y bar, so the mean of the y values. What are the residuals? Like what's the typical error here? Or what is the error? Just using y bar as a predicting value. So you know that the x values are unknown. We don't really know what those are at this point. So that column is just going to be blank. How many points do I have? 1, 2, 3, 4, 5. So I'll go down here. All right, so then we have some actual y values, which will go in this column. And again, I'm just trying to predict the y values. So I've got a y value of 2, of 3, of 5, of 4, and of 4. Now my predicted y values are just going to be the mean. I'm not creating a regression line or anything because I don't know what the x values are. So hey, my predicted y values are all going to be the same thing. They are going to be 3.6. If you average these values, you're going to get 3.6. Y bar equals 3.6. The average of these Y values is 3.6, like literally. So let me go with 3.6 here, 3.6 there, 3.6 there, 3.6 there, and again 3.6. Okay, so this next column is going to be our residual column. So hopefully you remember how to find residuals. It's about the easiest formula in the world. It is just y minus y hat, the actual value minus the predicted value. So if I did 2 minus 3.6, that's it. That's your residual, the actual value minus the predicted value. So the residual here is negative 1.6. Next residual would be negative 0.6. Next residual is 1.4. And my next two residuals are 0.4. Okay. That should do it for this. All right, so hey, one thing I'm going to do too is sketch where this line goes on our scatter plot. So y bar equals 3.6. All my predicted values are 3.6. So it looks like this line would be right around here. That's what I'm using to predict my y values. This one is 3.6. It's the average y value. All right, fantastic. So the idea behind least squared regression is all this error, these residuals, I can reduce that. I want to have the best predictor possible. Now, in order to do that, we are going to have some explanatory variables. So let me fill in the x values that are associated with these y values. That y value of 2 is associated with an x value of 1. This is data that I just kind of came up with for the example. And then we have 2, 3, 4, and gosh, what am I doing here? That's 2. All right, awesome. So by knowing these x values, I should be able to come up with a better predictor. I should come up with something that's going to reduce the amount of these residuals. So I'll make another column over here. Residuals using another table, residuals using, all right, so well, here, let's go like this first. I should probably set up the table. All right, so we've got x values, we've got the actual y values. We're going to need to find the predicted y values. And then we will finally find the residuals, y minus y hat, the actual minus the predicted. All right, so kind of repeating some more of this information up here. Maybe I'll say residuals using the least squared regression line. All right, so my x values were 1, 2, 3, 4, and 2. The y values are 2, 3, 5, 4, and 4. All right, so to get these this time, I'm actually going to be using my x values and the y values to get this. So my predicted, or my least squared regression line, y hat is equal to, I did this earlier, and so the regression equation is 1.846 plus 0.731, 0.731 x. Right, so I'm actually using the explanatory variable this time. All right, so kind of a process to get to this, but I just used a calculator for it, by the way. So one thing I guess we can review, to get the slope and the y-intercept for your regression equation, you would just go to stat, edit, go over to calculate, and then it's option 8 for linear regression. I am actually doing list 1 and list 2. Okay, and so hey, that's where I got these values, 1.846 and then the 0.73. I just rounded that up to 1. Awesome. So then I just went into my list, and hey, so my list 4 here, I just did that regression equation times whatever was in list number one. And anyways, I feel like I'm kind of rambling at this point. So hey, the predicted value here is 2.577. 2.577. My next predicted value is 3.308. Next predicted value is 4.039. So what that means, right, is if I did 1.846 plus 0.731 times 3, this is what the predicted value is, okay? And then next predicted value is 4.77. And then my last predicted value is 3.308. All right, fantastic. Now let's do the residuals, which would be this actual value minus this predicted value. So the residual for my first point is going to be negative 0.577. My next residual was negative 0.308. And then I've got 0.961. So the actual value minus the predicted value, my error there, like how far my guess was off, my prediction was off, was 0.961. The next one is negative 0.77. And the last residual for this least squared regression line is 0.692. All right, so the regression line then is, if I kind of try to plot these, my x value of 1 has a prediction of 2.577. So over 1, and I can go up 2.577. So here's where my prediction was. That's where my prediction was. And then my residual was, of course, negative 0.577. I did this actual amount and subtracted this predicted amount. All right, so I'll just sketch in this line as well. Looks like it might go like this. So we should start to see here that this green line is pretty close to all of these points, where this blue line, the mean, was very far away from like this point, right? It had a way large, or like a very large residual. We had a residual of 1.6 and 1.4, where all of the residuals here were less than 1, or at least less than the absolute value of 1. All right. So now let's actually get into the coefficient of determination. So the coefficient of determination is how much error we got rid of. How much error did we get rid of by using the least squared regression line to predict values rather than just the average y value? How much error did we get rid of? And then one more thing is, I know I mentioned this before in another video, but what we're trying to reduce is squared error. This is literally called the least squares regression line because it minimizes squared error. We are minimizing the squared error. Minimize the squared error. So we know that the error here is like negative 1.6. The error here is negative 0.577. But what we're trying to minimize is the squared error. All right. So like on our regression lines here, I have a squared error from this point. It looks like this to our blue line. But hey, going to that green line, going to the green prediction, my square is only this large. So hopefully you kind of see what's happening here. I minimized this giant square to just become this little square. Okay? Now, let's actually find the coefficient of determination. So r squared is equal to, or maybe I should just kind of write this out in words. It's the squared error. It's the squared error from y bar, from using this first set, or the residuals from this first set. So error, by the way, is just kind of like synonymous with residual. So if I say error or residual, I'm kind of referring to the same thing. So the squared error or the squared residuals from using y bar as a predictor minus the squared error from the least squared regression line, all divided by the squared error from y bar. So this is going to give us a percentage of error that has been eliminated, or squared error that has been eliminated. So hey, to do this, r squared is going to be equal to, all right, so I already got these values. I wrote them down somewhere. I can't remember where I put those, so I'll just start over. So I'll go to calculate, and so my residuals for y bar were stored in list number 3, and my residuals for the least squared regression line were stored in list number 5. So I'll go down to calculate, and so hopefully this stuff like looks pretty familiar to you. That does not look good. Where's my sum of my error? There it is. So hey, the sum of the squared residuals for y bar is 5.2. So 5.2. This squared error from the y bar, if I squared all of these residuals and added them together, I'd be getting 5.2. And then the sum of my least squared regression line's error is 2.4. So I'm going to subtract 2.4. This will all be divided by, standard deviation for y bar, which was 5.2. All right, so we're almost there. We've almost got our value for r squared. I'm doing 5.2 minus 2.4 divided by 5.2. And I get around 50 or 0.538. Approximately 0.538, or 53.8%. This is typically represented as a percentage. All right, so now it becomes like the actual important part here, interpreting this value, interpreting the coefficient of determination. So this 53.8%, what does it actually tell us? Again, it's how much squared error we got rid of as a percentage. So this is the interpretation statement. This is like the format you would follow to interpret coefficient of determination. So approximately, now we'll put our amount, approximately 53.8% of the variation in, so whatever your y variable is, like whatever you're measuring, essentially, your response variable, is it height, is it weight, is it GPA, whatever, approximately 53.8% of the variation in your response variable can be explained by your explanatory variable x. Approximately 53.8% of the variation in whatever the response variable is can be explained by your explanatory variable. Hey, so really the only reason that I went through this was so you had an idea of where this percentage comes from, where this value comes from. And again, just to like reiterate one more time, it is how much of the area of these squares, how much of the squared error have we minimized, have we got rid of? We went from this giant square down to this little one right here. So how much of the error were we able to reduce or get rid of by using the least squared regression line, which uses the explanatory variable? Remember, way back here, I didn't use an explanatory variable at all, and I got a total squared error of 5.2. By using an explanatory variable, I was able to reduce that squared error to 2.4, which means I got rid of 53.8% of the error, of my residuals. Okay, so good news is on your calculator, whenever you go to stat, calculate, and you come up with your slope and y-intercept for your regression line. All right, so I'm doing list 1 and list 2 here for my original data. and you see the value pop up right there. So I was a little bit off because I did some rounding, but I mean, 53.8% and 53.4%, that's pretty similar. If I would have used like all of this information for the slope and y-intercept and made these guesses more accurate, or these residuals more accurate, then I would have got this result. So anyways, you can get the coefficient of determination just from using your calculator. If you're able to find the slope and y-intercept, you should be able to find the coefficient of determination and even the correlation coefficient. So awesome. Yeah, I got this example I'm going to walk you through right here. So it's another one of those things where you're not really going to be expected to calculate that value by hand. You're just going to need to be able to interpret it. And the most common way is you're given a computer output from a computer program, and I'm pretty sure this one came from this program called Minitab. So when you run a report on Minitab, this is the output that you're given. It's the output that you're given from the program whenever you're doing bivariate analysis. So what do we have here? Wines are rated on a scale of 0 to 100 based on overall quality. Wine expert was curious if they could predict a wine's rating from its price. They took a random sample of wines. They noticed a positive. That's important. We need to know which direction this is. Noticed a positive linear relationship between their prices and ratings. Here's the computer output from a least squares regression analysis on their data. So I guess to be more specific, they are doing least squares regression, and that's why they got this output. Hey, so I guess one thing that we can do real quick is review how do you come up with the least squared regression line here. I know it's not a problem, but that's okay. So least squared regression line would be they're trying to predict the price. They're trying to predict the price based on the rating. So this coefficient column is where you get the least squared regression line. We've got 85.37 for the y-intercept. And then it was positive. That's why we're going to do plus this slope plus 0.07 times the input variable. So we're predicting price based off of the rating, the wine's rating. All right, fantastic. So that's just a little bit of a review how to get the regression equation from computer output. So hey, for question number 1, interpret the value of S in the context of this situation. So S refers to the standard deviation of the residuals. The standard deviation of the residuals, which is found just right here. S is literally equal to 2.70. So the typical error of predicted price to actual price is 2.70. I'm guessing they're doing that in like dollars, so we could put a dollar sign in front just to include some units. So the typical error, or the average error of the predicted price, I should probably say the difference between the predicted price and actual price is $2.70. That's all this means. Really it. So you interpret the value of R squared in the context of this situation. So R squared is equal to 40.1%. Real quick, sometimes on these things, you might see something that says R squared, and then in parentheses, it says adjusted. If you ever see this, just ignore it. That's for like multiple explanatory variables, which we don't need to worry about in AP statistics. So don't worry if you ever see R squared adjusted. Do not use that amount. Just use the R squared amount. So anyways, interpret the value of R squared. So this statement that I wrote down here is really the format that you can follow. So we'll say the amount approximately 40.1% of the variation. Approximately 40.1% of the variation in, so this is where we put our response variable, approximately 40.1% of the variation in price. That's what our response variable was being measured in. Approximately 40.1% of the variation in price can be explained by the Wein's rating, the explanatory variable. So by using the rating to predict the price, we've reduced the amount of error by, reduced the amount of squared error by 40.1%. So fantastic. Now, what is the value of the correlation coefficient? So the correlation and the coefficient of determination are related to each other. We know that R squared is equal to 40.1%, which can be rewritten as 0.401. R squared is equal to 0.401. I just got that from, of course, right here. So percentage to decimal. And hey, we also know that the correlation coefficient, its variable is R. So it should be really easy to get from R squared to R. All I'd have to do is find the square root here. So the correlation coefficient would be equal to, and yeah, I'll just have to do a calculator to do this, the square root, not mean to go there, the square root of 0.401. 0.401. There we go. All right, so 0.63 should be just about it. Correlation coefficient would be just about 0.63. Okay, so this last one is talking about a new kind of situation here. So a set of data compares the number of calories in a 12-ounce can of soda on the amount of sugar in grams and finds a strong positive linear association with a correlation coefficient of 0.78. Find and interpret the coefficient of determination. So it's really just going backwards from what we had here. We know that the correlation coefficient is just R, and then hey, the coefficient of determination is R squared. So it literally is the correlation squared. So if R is equal to 0.78, that would mean that R squared is equal to, I'm just gonna have to use a calculator for it, so 0.78 squared. Looks like our coefficient of determination would be about 0.61. Okay, so then the last thing here, so we found it, that's it, that's the coefficient of determination. Now let's interpret it. So approximately 61% of the variation in, so our response variable was number of calories, approximately 61% of the variation in number of calories can be explained by, whatever the explanatory variable is, can be explained by amount of sugar. All right, so those are the two things that I really wanted to accomplish in this video. Again, those two things were interpreting the standard deviation of the residuals. So just what's the typical amount that it varies by, the typical, I don't know, the average distance from our predictions to the actual amount. So I don't know, the standard deviation of the residuals is the average distance your prediction was off. That's all. Average distance that your prediction was off. So like for this example problem, the average distance from our predicted price to the actual price was $2.70. But you could say like with pretty decent confidence that our prediction was going to be within $2.70 of the actual price. Okay, and then the second thing was just be able to interpret the coefficient of determination, which was right here, the R squared. And again, that's just talking about how much variation can be predicted or can be explained by the explanatory variable. Okay, so that's going to do it for this video. Thanks everybody for watching. I'll see you in class. Okay, bye.